Welcome to another episode of Science Like Me. Today I have the pleasure of interviewing Tristan Brugère. Tristan is currently a grad student at UC San Diego. He got his master's in science in math and computer science from École Polytechnique in Paris, France in 2021. He is now a Ph.D. student in the Halıcıoğlu Data Science Institute here at UCSD. Tristan is part of the Institute for Learning-Enabled Optimization at Scale, also known as TILOS, one of the prestigious national AI institutes enabling longer-term research and U.S. leadership in AI. His advisor is the TILOS director, Yusu Wang. His research interest is approaching machine learning from a mathematical perspective. He is mainly working on optimal transport and neural networks on graphs, in particular graph generative models, with applications to chip design. Welcome, Tristan.
Thank you.
All right, so tell me about your research. What is it that you get excited about doing?
First and foremost, I'm like a math person. I come from a very math CS kind of background. So I came into like data science because I felt like it was a very empirical field of research, and it still is, and I kind of wanted to bring some kind of good like theory to that. So I tend to be more on the theory side of things. That's what kind of gets me excited about it. And yeah, as you said, right now I'm mostly on graph generative models, which is really interesting and kind of hard to approach. Which is, I guess, we come back to that. What gets me excited is like hard to approach projects. I want to feel like I'm making a difference, and probably like taking some projects that require my background and that are kind of hard to approach for other people makes me feel valued in a sense.
Nice. What is a graph generative model?
I guess I need to explain what a graph is first. Okay. So a graph is a kind of structure of data. So it's an object that is made of a set of things and relationships between these things. So, for example, if you're Facebook and you've got your social network is basically a set of people and friendships between them. Friendships in quotes. and those relationships are so you basically get a set of people and a set of relationships between those people, and that's definitely what a graph is. So other example is in chip design. A chip is a set of components that are linked together by wires. So the wires are the relationships between the components, and then you've got those small like logical nodes, logical gates that are linked together. And so it is fundamentally a very similar kind of object, which is kind of interesting, and which is what math is all about, like just putting a layer of abstraction and taking two very different things, seemingly like chips and people, and seeing, oh, but those things have this in common, so we can actually abstract over what they are and reason about both. And my work in graph generative models is making generative models like what we know, DALL-E or ChatGPT, that create like fake data and applying that to those kind of objects that are graphs, that are relatively complicated objects because they have this complicated structure of elements linked together.
Mm-hmm. So actually, speaking of ChatGPT, I did ask ChatGPT what was a graph generative model, and it said, and try to explain it to a middle school student. So this is how it explained it. It's, I think, similar to what you were just saying too. And correct me if I'm wrong or if it was a bad explanation, but basically if a child has multiple toys they like to play with and also outdoor games, the idea of a graph learning model or graph generative model would be connecting the kinds of toys they play with other kids who play with similar toys and might also like certain kinds of sports. So like they make all these connections between the sports they like to play or outdoor games with the kind of toys they like to play. Is it kind of a similar, and would that be too simplified of an analogy?
It's more like I don't really like this analogy.
Okay.
Mostly because in this case, you've got two types of objects. You've got like activities, toys, sports, and you've got kids. And you don't link the kids together, and you don't link the sports together. So you've got like you can consider that a graph because you've got a set of things that are linked together. But also you could consider that not a graph. Well, you could consider that a special kind of graph in that you can't link any two elements in your situation.
But what about the toys that they play with? Not necessarily the kids themselves, but just like you have kid A plays with a train and a teddy bear and also likes to play soccer. And it turns out that kid B also likes to play with trains and teddy bears, so it might suggest to play soccer. Like, is that the kind of, is that the graphing that this model does?
Not really, I think.
That's good. I mean, then I'm trying to understand. Okay, so could you use the toys and outdoor sports as a way to create a better analogy of how to use a graph generative model?
I guess if you wanted to do that, you could like forget about the kids. Your objects are, for example, the toys. And the kids would be like the link between the toys. So like there is a link between those two toys if there exists a kid that plays with both. Mm-hmm. And it would probably be interesting to look at that graph.
Okay.
In the sense that then you've got for example, so for example, the problem is that would be kind of a fizzy graph because probably for all two kinds of toys there probably exists a kid that plays with both. Mm-hmm. But like maybe if you do a bit of data, you could end up being like, oh yeah, so if your kid plays with this, they're still more likely to play with this because there is a link in that graph between those two, between those two things. But that's kind of an indirect way of thinking about your problem, in the sense that I don't know how natural this structure is.
So let's go back to chips. So you were saying how the connections you make with the chips is how the components are connected to each other. Is there also a layer of or data about the length of the wire, the width of the wire, like the placement of where the chips are in relation to each other? Is that any kind of data that gets fed into this graph?
Yeah. So for example, we were saying that the links, so the edges of the graph, as we call them, were the wires, and the nodes where for example, where the logical gates. So for example, the width of a wire could be what we call an edge feature, which is just some data associated with an edge. And the localization of a gate could be a node feature, which is, well, a feature associated with nodes. And so we get a sort of augmented graph, like that doesn't only have structure, but has data on that structure.
I mean, it sounds really complicated because from my background is actually electrical engineering, and when we built a basic circuit, like an LED circuit, you can position them almost in any way you want to, and it'll work. But when you work with really small devices, like something that would go on a chip, it's a whole nother level of complexity of trying to make this thing work. So somehow the work that you're doing is trying to figure out, like, modeling that level of complexity. Yeah. That's crazy. So I think that's crazy. It sounds really complicated. I mean, I also, apparently the analogy ChatGPT gave is pretty bad, so it is complicated. But where do you, how do you see in the pipeline of your research, like how does that apply everyday life, like everybody?
I guess my current project is trying to use those generative models to generate like fake chips, but that must be realistic looking. So we're not actually trying to generate something that works. The idea is that if we're able to, the idea is that chip data is really hard to get, mostly because it's all under intellectual property. And it's like the people who own it make it either very expensive or just not available. And so making new research on chip design is very hard. And clearly, like the research is lagging behind the industry. Mm-hmm. And to help solve that, the idea of this project is to create a lot of fake data that is realistic in a sense, but more than really good. Like, we don't require that those things work if you actually print them on a PCB. What you want is just that you're able to run, if you develop new algorithms in chip design, you're able to run these algorithms on this fake data, and that with a lot of this fake data, you'll be able to experiment and to benchmark how well your algorithm works, where it works well, in which cases it fails, why it fails. So our goal is to enable more research that will enable better chip design, that will in turn enable people to have better electronics.
Yeah, that's really cool. I think, so would your research...
It's a fourth degree impact, I guess.
Yeah, it's like in the very beginning stages, like the foundation of it, of sharing that with, people that actually end up designing the chips practically. They could use your research to optimize how they design a chip, right? Do you think, because I think if I remember correctly, the standard life cycle of designing a chip is like 18 months or something like that?
It's very long, mostly because a lot of the things in that pipeline are very long. Like we're talking steps of like optimization algorithms that literally take weeks to run.
Wow.
And on powerful hardware. And then the thing is, it's kind of fuzzy goals, which means basically what they do is they build a chip, then they try to optimize the placement, then they look at whether that would work. Like where are what they call design valuations. And so they go there, they look at basically where the chip would overheat or where there's something wrong, and they repair it a bit, and then they go back to square one or two, and they try again. And then they look at where it doesn't work, and then they try again. And they optimize like that. They'll do a little bit, and then they do a little step, and they rerun their very long pipeline, and then at some point they reach something good.
Yeah.
And it's a very empirical kind of process where the humans and their like intuition on how the algorithms will work and then what should make a good chip is very important. And so it's very hard to automate. And that's one of the parts where AI can come. And it's also very long, and that's the other part where AI can come.
Yeah, I heard I remember somebody asking, like, what does it take to train somebody to be able to do chip design, like out the gate, like just from education alone? But they responded with it also takes experience to I guess gain that intuition to be able to make the right choices.
I don't have that background at all. Like as I was saying, I'm from a math CS background. I started talking with people in the chip design field like a year ago when we started this project. And so like I'm describing what I see. Also, I'm absolutely not an expert in chip design or how it works. But I believe like my area of expertise, which is more on the very technical ML side, can be useful to them. So
that's actually really cool. I didn't realize that so you could have applied your mathematical analysis to a number of different kinds of applications.
Yeah, for example, graph neural networks these days are mostly used in chemicals or health kind of applications. So I was saying, oh, look, at a social graph can be a graph, or a chip can be a graph. What is also a graph? Things linked together, atoms linked together, molecules. Molecules are graphs. And the main application of I guess, at least the application you see the most in the literature on graph generation is actually molecule generation. People trying to develop new drugs, and they train those algorithms to like try to generate a lot of molecules that look like the molecules they know, and then they just test with heuristics and other things the properties of these molecules in hope of finding one that can work as a drug, as medicine.
Nice. Are you? So I have now two questions. Did you choose to do chip application? Like, was it something about that gravitated to you, or were you just like, give me any kind of application, I just want to do the math?
I clearly ended up in chip applications because my advisor was working with TILOS and with Andrew King's lab, and so it was kind of natural. And then I'm more interested in the math side of things, and I wanted, well, clearly to work with applications, because that's what makes like my work have meaning, is the fact that people are able to apply it to actual real life situations.
Yeah. Do you think the math that you develop in terms of analyzing this could also be used to apply to the molecule situation and creating new drugs, or does it have to be so you can extract it?
I mean, every advance on that technology, as long as it's like, as long as it's like good in terms of like, as it's not like a very specialized to the application kind of advance, as long as we're not adapting another like solutions meant for another solutions that already existed to this application, but we were creating the new solution in a sense, could be then applied to other fields.
Nice. So I want to actually go to the past. What got you interested in going down this path? What were you like in middle school or high school that made you realize that this was something that you wanted to do? I
was definitely a STEM kid. I think I got that from my family. Like, I was born into math in the sense that my mom is a math professor, and my dad is, well, he's got an engineering degree now. He's more of a management position. So clearly, like, yeah, I was pushed into it from, but yeah, even as a kid, I wanted to be an inventor. Yeah. Which I guess I never completely lost. And I got into computers, for example, because my dad at some point bought me a C++ book. Very, very bad language to start programming for the first time, C++. I mean, go talk about object-oriented and polymorphism to a 10-year-old kid, that doesn't work. Yeah. But anyway, and that's kind of what got me into computers, and also the fact that at some point he had me install Linux on my computer, and I stuck with it ever since. So yeah, I was definitely that nerdy computer kid, which was fun, yeah, in its own way. And then yeah, I got very into computer science, and especially in middle and high school, I was more of a computer science kid than I was a math kid. But my mom pushed me to go in this math prépa, so studies, which is a kind of like studies curriculum we have in France, and like that's where I started to actually like math. It's mostly because the kind of math you do in higher studies, especially in France, is very different from the kind of math you do in high school. It's a lot more abstract. It's a lot more puzzle-like in a sense. You're not just like learning some technique and applying that technique over and over. You're actually trying to like make proofs and reason and go out of your way. And it has that intellectual satisfaction kind of thing to it that made me like it. And that, yeah, in the abstraction and in the search for answers. Yeah. That you don't find at all from the kind of math you do in middle or high school. You already mentioned this a little bit, but you said you started playing with computer programming at 10. Were there other kinds of games that you played with that kind of encouraged you down the STEM path? I mean, at some point I had an idea of trying to like make a video game, but that never went through because. So yeah, I'm not really sure. No, I liked playing with like installing stuff and just taking care of like Linux computer a lot, breaking the OS, installing a new one, those kind of things. How many times did you break it? Oh, lots. Yeah, that's a good learning experience. At some point, I just decided to go through like every popular Linux distribution until I found the best one. Do not recommend. How many are there? Hundreds. Wow. But popular, fewer than that. But Linux distributions in total, hundreds, maybe thousands. I don't really know. How did you? I mean, I feel like I'm going to go down the rabbit hole here. But like,
That's an interesting, like, what would you do to test whether or not it was a good operating system?
Well, I feel like my definition of a good operating system changed along that path.
Okay.
In the sense that I settled on one that I'm still using now, which is Arch Linux, which is kind of fun because there's a meme on the Linux community, which is I use Arch, by the way, which is that people who use Arch and Linux will always end up telling you that they use Arch Linux.
Okay.
Because it had that simplicity in the sense that it's basically make your own kind of distribution. So you just have a very simple packaging system and you just install everything you're going to use, which in the end makes it very prone to breaking, but also very easy to fix. And to just understand, when you're working on that, you just understand how everything works and you get very good at fixing it until it doesn't become a problem anymore. Whereas when I started out, I just wanted things to work, but the problem is with distros that just work, is that when they don't work, you don't really know how to fix them, and you can go a very long rabbit hole.
Yeah.
Because they're not really made for that purpose.
How useful is knowing how to use Linux when working on programming graph generative models?
Probably not that useful. I mean, we have a Linux server we use to run experiments, but also I could know very little and use it.
Yeah.
It's a convenience to like know what I'm doing and kind of have an idea how the things work on there, but it's not really useful and not indispensable.
Okay, because my impression was from other data scientists that they generally do know how to use Linux when creating new models and whatnot. So I didn't know if there was like a relationship between knowing how you can.
It's more like the more you use it, the more you know how to use it, because those things are learned basically by breaking it and looking at how to fix it. And the more you use it, the more you look up how to do this, how to do this, how to do this, until you actually know how to do it. There might be like beginner like Linux classes, but the truth is mostly everyone just learns on the field.
Sure. So I guess what I'm saying is then, so if somebody wants to do research in graph generative models, knowing how to use Linux is not necessarily a skill set you need. You could also learn how to do this on a MacBook or a Windows system.
Yeah, but in general, you're probably going to end up not wanting to run things on your own computer because it needs a lot of power, which your own computer might not have. And even if it does, you don't want to burn your graphical cards for your research.
Okay.
Some people are not that dedicated.
Yeah.
And having like a laptop that just all day, not a great feeling.
Yeah.
So generally you tend to run things on like remote servers. Like our lab has one that we use to like run jobs and run experiments that have all the powers you need. I have no idea where that server is. Probably in the UCSD Computer Center, but the truth is I don't know.
Yeah, yeah.
And those servers generally run Linux just because it's way easier to like use remotely.
Yeah, okay.
So you end up interacting with it. The thing is, you don't need a lot of like knowledge to interact with it, and the knowledge you need, you can just learn it by doing.
Sure. How quickly do you think AI is advancing?
Very fast. That's for sure. Well, very fast, and also not as fast as people think, in the sense that a lot of it got publicly released, like recently, like DALL-E, like ChatGPT. So people suddenly have more access to it, which makes the whole society think, oh, this just appeared. This didn't just appear. Like, this is clearly the results of probably, well, tens of years of research that have converged to it. ChatGPT is not the first large language model. There were other GPTs before that. DALL-E is not the first image generation model, but it's clearly the first one that works that well. But like, they didn't just pop up, and they're advancing. It's advancing fast. Like, it's clearly a new science, and if you compare it to like physics that has been around for millennia,
yeah,
then yeah, clearly it's advancing very fast because we've got everything to discover. But also, yeah, it's still advancing at research space. Like it didn't just boom in the last year.
Yeah.
Is what I think.
Okay, well, thank you so much for coming for this interview, and I hope you enjoyed another episode of Science Like Me.